And welcome again to another training session of the NASA Engineering and Safety Center NESC Shock and Vibration Training Program. My name's Tom Irvine, and I'm an industry representative to the NASA Engineering and Safety Center via Dynamic Concepts Incorporated of Huntsville, Alabama. And we've been talking in the first two units about natural frequencies, about stiffness and mass properties, about the four main excitation mechanisms. And we're going to be finishing this unit today and doing a few MATLAB exercises. So we finished up last time talking about guidance systems and how there's concerns that structural vibration can interfere with guidance system algorithms. Now we're going to move on and talk about a different topic. And later on we'll have a webinar unit. We'll have several webinar units dedicated to shock. But I just kind of want to give you a sneak preview of the things to come and sort of get your mind thinking about things in terms of response spectrum, which is a very important topic in these series of webinar units. So this is a half sine pulse, and this is strictly for academic purposes. It's not intended to represent something that would actually happen in terms of a real-world environment. So along the y-axis we have acceleration in g, and the x-axis is time in seconds. And this particular half sine pulse is a 1g, 1 second half sine pulse. And let's think about now applying this as a base input to a single degree of freedom system. So I'm going to scroll back a whole bunch of slides. And earlier we talked about spring mass systems. So here we have a spring mass system, mass m, stiffness k, damping element dash pot c, and now imagine that the ground is shaking. So the ground is applying a base motion or base input to the spring mass system, and we want to know how that system is going to respond. And again, the natural frequency is the square root of stiffness divided by mass, and if we want to convert this to hertz, we divide by 2 pi. So now back to our half sine shock pulse. So we're going to apply this half sine shock pulse as a base input to a single degree of freedom system. But there are a few twists to what we are going to do. We're going to assume that the natural frequency of that spring mass system is unknown. It's an independent variable. So what we are going to do in reality is apply this to an array of single degree of freedom systems. And I'll show you that slide here momentarily. One of the things we want to determine is, does the peak response of a given single degree of freedom system happen during the half sine pulse, in other words from 0 to 1 second in this case, or does it occur after the half sine pulse is over during the quiet period? We also want to determine, is the peak response greater than 1g, in which case amplification occurs? Is it exactly equal to 1g, which is called unity gain? Or is the peak response less than 1g, in which case some attenuation or isolation effects are occurring? Now, the answer is, of course, it depends. It depends foremost on the natural frequency of the system, and to a lesser degree, but also an important concern, is the damping. So the damping will also have an effect on the response of the given system. So let's set up our single degree of freedom systems now. And this is leading into the whole idea of the response spectrum concept. And this is a concept that's useful for design and also for testing. So these spring mass systems are going to be independent of one another, and they're all connected to a common base input. And none of these systems has any mass loading effect on the base input. So the base input is its own independent variable. Now we're going to give these systems a common damping, and typically we would say 5% damping, which is equivalent to a Q factor, an amplification Q factor of 10. And we'll talk about damping a little bit more later on. But for now, just realize that all these systems have the same damping. And you might ask, well, what's so important about Q is equal to 10? Well, at this point, you're just going to have to accept that it's an industry convention. And if we happen to know what our damping is, for a given system, then by all means we can use the proper Q. But just as a sort of a default industry-wide assumption, we're going to assume Q is equal to 10. Now, a way to think of these is that they're arranged in order of ascending natural frequencies as we go from left to right. So just for simplicity, consider that all these masses are the same. In that case, in order that they have ascending natural frequencies, the stiffness of these springs must vary as we go from one spring to the next. So over here we would have a very compliant spring. You might say it's a soft-mounted system, or we might even say it's an isolated system. And as we go progressively to the right, the stiffness of the spring continues to go upward. And by the time we get to the system on the far right, this is almost like a rigid link. And for any of you that do finite element modeling, you could think of this as like an RBE2 element. So what's going to happen? Well, we'll see in a minute when we apply that half-sign base input. And by the way, these I've shown the natural frequencies here, and I've arranged them in 1 octave steps, so we increase by a factor of 2 each time we go up. And this is just somewhat arbitrary, and it makes for a good educational demonstration. If I was doing this on actual test data, I might even have like a 1/12th octave step. But again, this exercise is purely academic. So I've got a video here, and I'm going to pull up the video and show that to you here shortly. And it's one we're going to spend some time with because it's a really important one. And it's called hs_srs.avi. So let me call this video up. So we're going to apply the half-sign pulse. Now each system has its own unique response to the base input. That depends on each system's natural frequency mainly, but also its damping. So you can see there we're well into the quiet period. The half-sign pulse is over, and those systems in the middle are still vibrating. You might say they're undergoing reverberation if you want to use an acoustic type term and apply it to structural vibration. So we've got our reverberating systems right in the middle. In some sense, we could say this is resonant excitation, but the excitation itself has passed, and now it's actually in free vibration. Okay, we're going to look at the system on the far left, and let's see what does it do. So during the half-sign pulse, that mass, it's not quite stationary, but there's very little motion for that mass on the far left system. Well, when I say very little motion, that's true for the mass, but what about its spring? So here we have this soft-mounted system, and let's see the half-sign. That spring undergoes quite a bit of compression, or we could say relative deflection. So the absolute motion of the mass is minimal, but that spring does undergo a high relative displacement. Let's go to the system on the far right, and what you'll see is it's, relatively speaking, it's a hard-mounted system, and the mass itself is very nearly tracking the base input. Its spring has very little relative deflection. So that's its characteristic. What about the systems in the middle? So this middle system, it has a very high displacement of the mass, and it has a very high relative deflection of the spring. In fact, it's probably the highest in each of those two categories. So this is useful for design purposes, and later on it's going to be useful for testing too. And the way we look at these shock response spectrums is we're going to calculate the time history response of each mass. And after we calculate the time history response, we're only going to retain the peak positive and peak negative acceleration for each of those masses. So in other words, we're going to calculate the complete time history for each, but we're going to throw away each time history except for the peak positive and the peak negative amplitudes. And then later on, or as the next step, we're going to plot those as a function of natural frequency for a given Q factor. And once we do that, we're going to have a plot called a shock response spectrum. And we're going to cover a shock response spectrum in earnest in an upcoming unit. But for now, I just want you to get a feel for what the basic concept is. So let's think about this a little bit more. How could this be useful for design purposes? Well, if we want to minimize the acceleration and displacement of the mass in terms of the absolute values, in other words, the absolute acceleration of the mass, the absolute displacement of the mass need to both be minimized, we would want to mount that on a very soft spring. So it would be almost like it would be an isolated system. And that's all well and good, but we need to make sure that the isolator can withstand the expected maximum relative displacement without bottoming out. So bottoming out is one concern anytime we isolate. We also may be concerned about sway space and clearance and whether or not this mass might have an impact with some other nearby mass or subsystem or component. And sometimes we also need to be concerned about components that need to maintain a physical or optical alignment with some other component too. So there are some cases where it's not advisable to isolate our components, but particularly for avionics components in rocket vehicles, we tend to like to isolate things as much as we can. Well, what if we're concerned about minimizing the spring displacement and we're allowing the mass to undergo some amount of absolute displacement? Well, in that case, we'd want a hard mount. So let's look at the hard mount system. So we're going to allow the mass to track the input with a unity gain. We're going to say that's fine after all, because we're concerned about minimizing this relative deflection. Well, there's some other concerns we might have too, and if you deal with avionics components on launch vehicles, you'll come across things like C-band transponders and telemetry transponders or telemetry transmitters, and these tend to output a lot of heat energy, and that heat energy needs to be dissipated. So maybe that avionics component is mounted on a metallic bulkhead which serves as a heat sink, and it needs to be hard mounted for maximum heat transfer effects. So for those type of components, the thermal considerations in many cases would outweigh the vibration and shock type concerns. There's also components we've kind of talked about earlier, like inertial navigation systems that have their own control algorithm, maybe a servo mechanism of some sort. And the vendor of these components may be assuming that they're hard mounted. So if we take such a component, could be an inertial navigation system or even a hard drive, and we want to mount it via isolators, we need to make sure that it's not going to interfere with any control algorithm or cause any instability. So we need to check that over with the vendor. In many cases, inertial navigation systems already have internal isolators for their sensor heads. So if we isolated the outer portion of the box, we'd effectively be making a two-stage isolator, which may or may not cause some problems with the control algorithm and its accuracy. So check it over with the vendor if there's any doubt. Okay, what else do we want to say about these? Well, in many cases as we go through life, moderation is a good thing. But in this case, a moderate natural frequency would be a bad thing for this particular half-sine pulse and this particular family of natural frequencies with their damping ratio, their common damping ratio. So in this case, we'd either want to be one way or the other. We would either want to soft mount our system, maybe via isolators, or we would want a very stiff system. We've already seen an example of where a stiff system is advisable, and that's the case if we're mounting a satellite payload into a Pegasus launch vehicle. We want the natural frequency of the payload's own cantilever mode to be 20 Hertz or higher per the payload user guide. So situations vary, but that's just a little kind of a brief introduction into a shock response spectrum, and we'll also be covering vibration response spectrum in an upcoming unit. And I want to show you just a fun little detour on the blog. So if we go to Vibration Data Blog, and let's just go up to the search box, and let's put in Isolator Gallery. Isolator gallery. I've got some photos of some isolators, some things you might be familiar with. Well, this one's pretty unique. We're going to start off with. This is actually an isolated component on a launch vehicle. And if you look off to the left, you can see some funny writing. It might even look like Russian writing there. And this happens to be a Scud-B missile. Well, how did I get to see this? Well, in Huntsville, Alabama, there was a public display of military equipment, and here was the Scud-B missile, and the access panels were removed so we could see down into the avionics. So here's some avionics box, not sure what it does, but it's an avionics box, all right. And it's mounted on these little elastomeric or thermoplastic or rubber isolator bushings, or sometimes they call isolator grommets. And the idea is that these will break metal-to-metal contact. And if they do that, they can provide isolation for both shock and vibration. So this is the way we like to go as often as we can when we're mounting avionics into launch vehicles. Now, one thing quite unusual about the Scud-B is that this instrument shelf here and this portion here, they're both made out of hardwood. So I thought that's funny. It's organic material, and I was thinking about that. Well, maybe that has really good damping properties. But all the instrument shelves or bulkheads I've dealt with in the past, they've been typically honeycomb, sandwich type construction with aluminum face sheets, or in some case just homogeneous aluminum, or maybe in some case composite material, carbon fiber, epoxy type carbon material. So I thought that was just interesting. And you might say, well, how come I'm showing a picture of a Scud-B missile instead of a U.S. launch vehicle? Well, U.S. launch vehicles either are classified or proprietary or for official use only, or can't show to foreigners or whatever. So don't have any of those pictures available. But some of you that work on U.S. launch vehicles have certainly seen those. Okay. Another benefit of isolators is that they tend to render the system as a single degree of freedom system, and that's very effective. And we'll talk about that more in a later webinar. Well, some of you might have 4x4s, or even just an ordinary automobile has shock absorbers. And if we think of the body of the car as a rigid mass, and then we take these suspension components and put them all together as a spring, the spring mass natural frequency of a vehicle tends to be about 1 Hertz to 2.5 Hertz. Of course, it depends on the model type and whether it's designed for off-roads or just general passenger comfort. And these shock absorbers tend to produce about 33% viscous damping. So it's a well-damped mode. And later on in one of our course units, we're actually going to look at some automotive accelerometer data, and we'll see that those two statements are correct for just a regular passenger car. And here's something that's really fun. If you ever go down to Tucson, Arizona, and go away south to a place called Green Valley, you can actually take a guided tour of a Titan II missile silo. And this is a launch control room. You can go down and see, and this control room is actually mounted on springs, and these are these springs are designed to allow 18 inches of relative displacement. And so these springs were isolating this underground control room. And the idea was that if the enemy launched a missile attack, a preemptive missile attack on this site, that this control room would remain intact, and the control room could then fire off a retaliatory strike with a Titan II missile. So that's pretty interesting if you're interested in Cold War history and all that. And another thing that was interesting is that this missile museum was right next to a mining site, and mines use explosives to break up the rock material. And I was thinking to myself, and I asked the tour guide, well, what about the seismic energy propagating from the mining explosives? And the statement was, hey, these things are designed to to withstand a direct missile strike. Mining explosive shock that propagates here was down in the noise compared to what these things are built to withstand. So anyways, if you like Cold War history or rockets or anything, you get down by Tucson, Arizona, encourage you to check that out. Here's my colleague Robert Towner. He's standing on the USS Alabama. It's a World War II era battleship. You can take a tour. It's docked down in Mobile Bay, Alabama. And he took some pictures. He noticed that there was some different springs on the piping system, so we got some pipe hanger type springs designed to isolate the pipes, and you can see a pair of springs there. These ships might be subjected to torpedo strikes or strikes from aircraft, bombs, rockets, whatever. So they have to be designed to operate in the event of an attack. So these are just some kind of fun photos of different isolating systems, and if any of you have some photos you'd like to send to me with other types of isolators, I'll post them on this page and give you credit if you like. So let's see, where are we now? Let's go back to the shock response. Actually, we're finished up with the shock response spectrum now. And the next thing we're going to do is some exercises. And these will be MATLAB type exercises. So I'm going to make this full screen. And okay, we finished up with that. So let's say we have a particular circuit board, and it's modeled as a single degree of freedom system. It weighs 0.1 pounds, that's LBM. Its stiffness is 400 pounds, that's LBF per inch. And we can calculate the natural frequency. Well, the natural frequency formula, we've seen that previous. Go back a number of slides. It's going to be equal to the square root of the stiffness over the mass. And this would be the radians per second angular frequency. Then we divide by 2 pi to convert that into hertz. So you might think we could simply plug in the value for k and the value for m and away we go. Well, that might work if we had metric units or otherwise consistent units, but it's actually a little tricky because we're going to have to account for a factor of 386 because the weight is in LBM, that's pounds mass. The stiffness is in pounds force, LBF. So one way or another, we're either going to need to divide or multiply by 386, and I'll let you figure out how to do that yourself. But let's go to vibration data, and well, let's go to our MATLAB command window, and I'm going to type in vibration data. And again, this is the main script suite that we're going to be using in this class, these series of webinar classes, and you can freely download it from the vibration data blog. So let's type in vibration data, and we're going to do the case of, let's go over to miscellaneous and structural dynamics. Let's begin the miscellaneous analysis. Let's do a single degree of freedom system natural frequency. And got a little glitch there. Single degree of system natural frequency, perform. And we're going to calculate the natural frequency. And we're going to do that by putting in, what did I say, 0.1 LBM. That's the circuit board mass. And the stiffness, if I recall correctly, was 400 LBF per inch. That's pounds force per inch. So we calculate this, and we get a natural frequency of about 200 hertz. We also see the natural frequency in radians per second unit and the static deflection at 1G. And if we wanted to, we could copy and paste these and paste them into a Word document, for example. So you're welcome to do the hand calculation, and I encourage you to do that just to get the experience. But then you're also welcome just to use this software program to check your work, or as the primary way of doing the calculation. Let's do another example. Let's say, I'm just going to make this up. We want to have a system that's isolated at 25 hertz. And it happens to be, let's go ahead and say it's a really heavy item. So it's a 400-pound mass item. We want to isolate it at 25 hertz. What should the stiffness be? Well, the stiffness should be, there's the LBF pounds force per inch value, about, I'm going to round up and say 26,000 pounds force per inch in order to achieve 25 hertz at 400 pounds mass. Now, if this mass was kind of a rectangular box-shaped article, we might have 4 different springs at each of the 4 base corners of that box. In that case, we'd take this total stiffness and we would divide by 4 to get the desired individual spring stiffness. So those are just a couple of different ways that you can use this script to do some calculations. So we've got a couple other things that we can do as well. One of the things we can do is a beam calculation. So let's go to the structural dynamics, begin analysis, beam natural frequencies. A little glitch is coming up, annular underscore plate dot bending. I don't have the latest version of my own software here, but if you download the latest version of the software, this little glitch won't come up, and you can go directly to the beam frequency. Okay, so the left, let's just make something up. We're going to have a beam. We're going to calculate the bending natural frequencies of a beam. We'll say it's fixed free. So the left boundary condition is fixed, the right one is free. So we're going to have a cantilever beam. We'll do English units. We'll make it 36 inches long. We'll do, let's do a solid cylinder cross section. We'll make it an inch diameter. We're going to select aluminum, so there's already a material library of sorts. So we see the elastic modulus and the mass density. We're going to calculate the natural frequencies. So the natural frequency for this rod, you could call it, which is fixed free in a cantilever manner, is 21 Hertz if we round off. And then you can see the higher natural frequencies there. Then we can take a look at the different mode shapes. This is the fundamental bending mode, and you can see it's fixed at the left side. We've got the second mode, and in this case there's a nodal point here. And at this nodal point there is rotation, but there is not translation. So in terms of translation, this point on the beam will always be fixed for pure second mode bending. Then for the third mode here, we get a nodal point here, another nodal point there, and then so on to the fourth mode. So these are just some things you can do for beam calculations. You can also apply base excitation, and we're going to do that in a future unit, but not now. And you can play around with different cross sections and materials. If you want to find out about more about beams, and you're the type of person that likes to get into the formulas, which is, it's always a good thing, is to get into the formulas and familiarize yourself with them. I've got a tutorial that you can download, and you can actually get this off my blog. And let's see. On my blog, if you just do a search on beam, you can get to the tutorial. But I actually want to show you a PDF document. It's the same document you can get from the blog. And the reason I'm going to do this is because when it opens up in an internet browser, some of the fonts get a little messed up. But if you download it as a PDF, it's easier on the eyes. So if I go to C, vibration data, tutorials here, and we're going to go to beam.pdf. So I've got a whole bunch of versions of it, a bunch of other things going on here. So if I go to fumbling around a bit here, beam.pdf, okay, here we go. So this is bending frequencies of beams, rods, and pipes. And the first table I have is I show what the natural frequency formulas are. For some of the common beam configurations, cantilever beam with end mass, simply supported or pinned at each end, a free beam, fixed beam, fixed pinned beam. So you can see what the formulas are to calculate the natural frequencies, and those are the formulas that are embedded in the vibration data program. And then some of you might say, well, how are those derived? Well, in some cases by the Rayleigh method, or some cases by the energy method, or actually directly solving the fourth order governing equation of motion and coming up with some mode shape function in terms of sines and cosines and hyperbolic sines and hyperbolic cosines. And in some cases, to get these natural frequencies, we actually have to solve for the roots of a transcendental equation and use the Newton-Raphson method or some other numerical method. But if you go on to the different appendices, you can find the derivations, the equations, go through the derivations yourself as you like, and go through all the formulas and equations. So I'm just kind of skipping through these quickly right now. There's also some information on participation factors and effective modal mass. And those types of parameters are important for the case we're doing base excitation. So again, that's beam.pdf, and the way you can download it is if you just go to the blog, as I mentioned, and probably just type in beam. And I've got the first one that comes up is beam bending finite element analysis. We'll cover that in maybe some future unit. So here we have beam or rod longitudinal natural frequencies. Well, actually we're concerned about bending frequencies, but you can get the formulas for the longitudinal modes from that link. So here we have beam bending frequencies and mode shapes, and here's a launch vehicle. And as these vehicles launch, during their powered flight, they're free beams, and they undergo free body bending type vibration. And that can actually interfere with the control algorithm, so we have to carefully analyze that. And that we also measure the vibration in flight to do post-flight data reduction. But if you scroll down here, you can see that the paper I was referring to is available via this link. And some of you that might want to get into other beam cases, there's multi-span beams, beams with axial loads, and a few other things as well. So you can just browse through that at your leisure. So that's beams. Now we can do other things too with this signal package here, this vibration data signal package. We can do other structural dynamics things. We can do, for example, rectangular plate. And with rectangular plate, we can either have a homogeneous or we can have a honeycomb sandwich construction. Just for simplicity, let's pick homogeneous. And we can do, for example, I'm going to pick English units, simply supported boundary conditions. And these will be, by the way, this will be for the calculation of the bending natural frequencies. And then, okay, a little glitch here. I'm actually on an annular plate. An annular plate is actually it's a circle with a circular cutout in the middle. Okay, so we're doing annular plate. We'll go back and do rectangular plates in a minute. Here's the annular plate. We're going to make it out of aluminum, and we'll say 48 inches outer diameter, 24 inches inner diameter, thickness of 1. And for the annular homogeneous plate, we get a natural frequency, in this case fundamental, of 664 hertz. And the second mode is at 694 hertz if we round off. Later on, I'll show you in a future unit a finite element application where we can actually visualize the mode shapes for this annular plate. We can also add non-structural mass, and this will be mass that is uniformly distributed. So let's say we add 40 pounds of non-structural mass uniformly distributed. That would drop the natural frequency down to 583 hertz. So that's for the annular plate. We can do circular plates. Okay, circular plates perform analysis, and we can do honeycomb or homogeneous. So yeah, maybe we should go ahead and do a honeycomb plate. I've been in working on launch vehicles that had a honeycomb sandwich circular bulkheads, and the avionics were mounted upon those bulkheads. Face sheet, typically aluminum, so the aluminum properties there. The core mass density, we'll get back to that one in a minute. Let's say our diameter is 36 inches. Top face, maybe 1/10 of an inch. Bottom face, again at 0.1 inches, 1/10 of an inch. Core thickness, we'll make it 0.8 inches core thickness. The core density is going to be much less than the face sheet density because it's honeycomb. So let's put in a core density of 0.0. We'll say it's 1/10 as much. You can go to a vendor catalog like the Hexcel company makes honeycomb and get some precise values for your particular application. 100 pounds non-structural mass. What's the natural frequency of the circular bulkhead? 187 hertz is the fundamental frequency. And a lot of the bulkheads I've dealt with have actually had lower natural frequencies. So let's say that it was a 48-inch bulkhead. Let's see what happens. Natural frequency drops to 129.6 hertz for the fundamental. Okay. What else might we do with this? Actually, it looks like we have 100 pounds non-structural mass and a 50-pound bulkhead, and oftentimes bulkheads are actually weigh a bit less than that for the ones I've dealt with. But so maybe our face sheet thickness should be smaller. Maybe let's do 63 thousandths of an inch. Maybe let's see what happens if we have thinner bulkheads, face sheets, that is. So then the natural frequency drops to 100 hertz. Well, you can play around with this at your leisure. Now let's try rectangular plates. Okay, again, if you have the latest version of the vibration data software, the angular plate will not automatically pop up, but I'm actually using an older version. Let's go to rectangular plates, and let's make boundary conditions. We'll make it pinned, which is, you might say, simply supported all around. Just to be different, let's do steel, and the width will be 6 inches. Thickness will be 1/8 of an inch, 0.125. Length will be 18 inches. So here's our rectangular plate. We see the material properties there. We have options for putting in the mass density, and well, the mass density would be from the steel, or we could do other if we had a unique material, or otherwise change that. We could put some non-structural mass. First, I'm just going to leave non-structural mass at 0. Let's calculate, and that's 373 hertz for the fundamental mode, and the total mass just of the bare plate is 3.78 pounds. So now let's say this has to support 10 pounds of uniformly distributed mass. Well, in this case, the natural frequency would be 195 hertz. So please play around with this, and for your own problems, you can vary the boundary conditions. If you look at all the permutations, we do not have formulas for all of the permutations. We do for most of them, and most of the common ones, but there's a few we do not. And if you come up with a case with irregular boundary conditions, then we need to do a finite element model, or maybe a Rayleigh-Ritz method or something like that. So anyways, under structural dynamics, you've got a couple of things you can look at, different natural frequencies. And you might say, well, every time I do an analysis, I have a complex structure, I have to do the finite element method. Well, that's all well and good, but it's good to just do a sanity check. So if you can simplify your system into a beam or rectangular plate or circular plate or annular plate, this is a good tool just to do a sanity check on your finite element analysis. Let's do one other thing. Do you remember we had the Tacoma Narrow Bridge a while back? So I'm going to go to the Tacoma Narrows Bridge, and we said that the peak-to-peak displacement was 28 feet. And at 0.2 hertz, and that was the torsional mode right before the failure occurred. So I'm going to say 28 feet, 0.2 hertz. Well, the first thing I want to do is convert 28 feet. This is peak to peak. We always need to be careful about our amplitude metrics. We'll assume that's 28 feet peak to peak. And let's make that equal to, I've got some other calculation up there you can just ignore. So that's going to be 336 inches. That's the equivalent to peak displacement for the torsional mode at 0.2 hertz. And this is, again, Tacoma Narrows Bridge failure. So let's go back to this vibration data software, and we have we can do different things with amplitude metrics. So we're going to have over to miscellaneous amplitude conversion utilities. So let's click on amplitude conversion utilities, begin miscellaneous, and we're going to go to steady state sine amplitude. Now we're going to enter a displacement, and it's going to be a peak-to-peak displacement. It'll be in inches, and the number is going to be 336. And the frequency is going to be 0.2 hertz. So the question is, what is the equivalent velocity and acceleration for that point on the Tacoma Narrows Bridge that was undergoing 28 feet peak-to-peak displacement? So we do a calculation, and if we round up a bit, it was 0.7 g acceleration. So at 0.2 hertz, considering that frequency, yes, that is quite a bit of acceleration. The velocity was 211 inches per second, and as velocities go, that was a very high velocity. So this is just a utility. If you anytime you have steady state sine vibration, and regardless of whether it's you're measuring the forcing energy or the natural response, a natural frequency, or a natural frequency excited by resonance, whatever sine vibration that you may have, if you know the displacement, you can calculate velocity and acceleration. Or if you know one, whichever one you know, you can calculate the other two amplitude metric types. And then displacement, sometimes we have displacement as peak to peak, and sometimes we have displacement as 0 to peak. So both of those are in there. And you can take these metrics, equivalent metrics over here, and you can do a Control-C, and then you can go into your WordPad or your Microsoft Word or whatever you might have, and just do a Control-V, and then you can paste the results as you like. So that's just another little couple things you can do with this vibration data signal package. And as we go on to future units, we're going to be talking about all these other goodies: Fourier transforms, fast Fourier transforms, waterfall FFTs, on down to Bessel filters, mean filters, and so on. And we're also going to be doing some things with power spectral density functions as well. So fun times ahead. And also I'm oftentimes upgrading the software, adding new features. So if you have some function you'd like to see added into this software, please let me know, and I'll see what I can do. And I think that actually concludes our unit on natural frequencies. I had an exercise. Okay, here's a flagpole. It's a cantilever beam. Look at the mode shapes. And that's kind of similar to what we already did with our beam analysis, only we used a 36-inch beam instead of a flagpole. And later on in the first unit, the very first piece of data we looked at was the tuning fork data. Okay, so we're going to close out of the natural frequency unit, but certainly we're going to be talking about natural frequencies as we go along. We're just going to spend about 10 or 15 minutes talking about shaker table testing. Now, shaker table testing is important for avionics, and it's also used any kind of equipment to be mounted in a military vehicle or automotive industry or ship or whatever, launch vehicle. Even for large shakers, sometimes scale models of buildings will be placed upon them for an earthquake simulation test. And these are done on shaker tables. And the most common one for avionics components is an electromagnetic shaker, or also called an electrodynamic shaker. And this is, sometimes we test things as large as satellite payloads or space probes. Other times we test things as small as like a little RF coupler or RF splitter or divider that's not much bigger than a book of matches, and everything in between, all sorts of shapes and sizes and masses in between. So this shaker table provides, in this case, a single axis vertical oscillation and base input or seismic input, in this case to the satellite payload. Then these shakers can also be rotated 90 degrees and attached to a slip table, and then the test article can be put on the slip table and then subjected to vibration in its lateral axes. So this is conceptually what's going on with a closed-loop shaker table test. So we have a control computer here, and later on in the units we're going to simulate as if we were the control computer, or if we were trying to write software for a control computer. But the control computer outputs a voltage, or you might say current, time history. So we may have a test spec that's a power spectral density, or it's a shock response spectrum. Well, there's no way for this control computer to output a power spectral density or shock response spectrum directly. So the control computer has to come up with a time history. We say it has to synthesize a time history to match this spec, and that's what it outputs in the terms of a voltage signal to the power amplifier. So the amplifier does its thing and outputs a signal to this shaker, and typically it's an electromagnetic shaker, and it has a field coil and an armature. If you look around enough, you'll find there's all sorts of other hydraulic and pneumatic shakers, but mostly we use electromagnetic shakers. And then there's a fixture. It serves as an adapter, and the test article is mounted onto the fixture, typically rigid mounted. And here's the accelerometer. Now, if this were an actual test, there'd probably be at least 2 control accelerometers. But for simplicity, I'm only showing one. So this accelerometer, this is the feedback loop. So the control computer, it wants to attain a certain vibration level on this fixture. So it verifies that via the control accelerometer, and then it adjusts its output accordingly. So it has real-time updating of the drive signal. And actually, the way these tests start out is that typically the control computer would just put out just a very, very small millivolt range signal, just to barely excite the shaker. And then it gets the response signal, and it has to calculate the transfer function and the gain factor for this loop. And that has to be a function of excitation frequency. And then we don't try and do the full level all at once after we've done the control loop check. Rather, this will start at minus 12 dB maybe, and step up at 3 dB increments, each time recalibrating the gain factor for the control loop. And that's to account for any nonlinear behavior occurring in the control system as we step up to full level. So again, we're going to have some fun in later units synthesizing time histories as if we were the control computer, or we were writing software for a control computer. I talked about that already. Conceptually, the shaker table is similar to a loudspeaker. Now, there's all sorts of reasons we might want to test an item. We might do, for example, a qualification test where we verify the integrity of the design with respect to the maximum expected level, along with some very generous safety factor or statistical uncertainty margin, whatever you want to call it. And in the case of avionics for a rocket vehicle, we would take one component that it would be a non-flight unit. It would never actually fly. We would test it to its qualification levels to test its design to make sure it was a good design. Now, then for the actual flight unit, which would be the same part number but a different serial number, we might do an acceptance test to verify the parts and workmanship, such as the solder joints and lead wires, because otherwise latent defects might occur as the box is actually subjected to vibration in flight. And in addition to verifying that the avionics box has good parts and workmanship, we also need to verify that this test level envelops the maximum expected flight level. But this qualification level in number 1 would be maybe 3 to 6 dB higher than the vibration level for the actual flight unit. And there's different cases. Sometimes we have one of a kind satellite, for example. It has to undergo a vibration test. So if we test it to the qualification level, that might be too high. If we test it to the acceptance level, that might be too low. So we do a proto-flight level somewhere in between, and we do a lot of cringing when we do that because the act of testing itself is causing some accumulated fatigue cycles but yet we want to make sure there's no latent defects either. So that's always agonizing. There's variations on this theme. Sometimes there's what are called lot acceptance tests. Let's say, for example, you have some explosive devices, pyrotechnic devices to go on a rocket vehicle. Well, so you want to subject it in vibration, but then if you want to see if it still works after vibration, you have to set the explosive device off. You have to detonate it. Well, when that happens, it can no longer be used because you've just used it up. So there may be a lot of 100 different pyrotechnic devices, and then some 5 or 10 of those, whatever, will be subjected to qualification testing, or what's actually called an equivalent lot acceptance test, even though it's probably at qualification test levels. Those units will be tested and then detonated to make sure that they can still perform their function. And then after vibration, and then at that point we'll say, well, the other 90 or so units are good to go based on the fact that we had 10 units that passed lot acceptance testing. And I'm sure there's different variations on these themes depending on whether you're in the automotive or shipboard, or you work on railroad engines or whatever, consumer electronics. There's variations on these themes. But those are just some ideas. And of course, there's different specifications that come into play. Some of you may be familiar with Mill Standard 1540 or the various Aerospace Corporation follow-on standards, or maybe you've done Mill Standard 810 type testing, or you have some other spec that governs what you must do. We can also do shaker table tests to evaluate natural frequencies and transmissibility ratios, realizing that most likely that'll be a hard-mounted component, and taking that into effect. One of the things we might do, particularly for a shaker table test in this regard, is we might put in various input levels, and that's to evaluate linearity, because sometimes damping or stiffness can have a nonlinear behavior as levels increase. We might do a shaker table test to evaluate the effectiveness of isolator mounts. And sometimes we'd even say, okay, these isolator mounts have to withstand extreme cold or hot temperatures, so we might actually mount a thermal chamber over the shaker, or mount the shaker under a thermal chamber, whichever the case might be, and would test the isolators at different temperatures to see how the natural frequency of the isolated component would change. I guess a particular concern is more the cold temperature, where these isolators might become hardened, and they would lose their compliance, and the natural frequency would go up. And that would be typically the case for some rubber or elastomeric thermoplastic type isolator. And if that's the case, we might have to do something like a wire rope isolator. Okay, what else do we have here? In most cases, it's a good rule of thumb to power and monitor the electronic components before, during, and after the vibration test. There could be some unique failure modes that occur only during the test, during the vibration, but not before or after. And this may be a bit hypothetical, but imagine if we have two parallel circuit boards and they're vibrating out of phase with one another, 180 degrees out of phase, and thereby they might impact, they're creating an electrical short which is present during vibration, but not before or after. So certainly if the component must perform its function during vibration, it should be powered and monitored during the vibration test. That is, if it must function in the field environment, under field vibration environment conditions. I think another good reason to do this is, let's say you've got a 1 hour per axis long test on the component, and something happens, one of the lead wire breaks 5 seconds into the test. Well, at that point you can save a lot of time just by stopping the test and then going and doing your failure investigation. If you wait too long, something else might happen or whatever. So it's good just to be aware right away if the component is failing during vibration test. So what else? And actually that concludes the unit for now for the shaker table testing. And if you come back for the next unit, we're going to be talking about sine vibration and response to sine vibration, And then in future units, we'll be talking about random vibration and non-stationary vibration and Fourier transforms and power spectral densities, shock response spectrum, and all sorts of other structural dynamics. We'll even get into things like rain flow fatigue and fatigue damage spectra. So have a good day, and thanks for tuning in. Goodbye.